Hello everyone, I am Tsubasa Shoshi from the University of Tokyo. Today, I'll talk about our research, termination analysis for the pi calculus by reduction to sequential program termination. The pi calculus is a concurrent computation model. There have been studies on termination analysis for the pi calculus. However, most of them are theoretical. There have been little effort in developing fully automated termination verification methods and tools. As far as we know, typical is the only verification tool, but its termination analysis is quite limited. Now, we propose an automated method for proving termination of pi calculus processes. We translate a pi calculus process to a sequential program so that if the transformed program is terminating, then the original process is terminating too. Our approach enables us to use powerful tools developed for sequential program termination. We have implemented a termination analysis tool for the pi calculus based on the proposed method. This is the outline of the presentation. First, let me introduce the source language, the pi calculus. The pi calculus is a concurrent computation model where processes are interacting with each other via communication channels. The syntax of processes is defined like this: in action, output, input, replicated input, parallel composition, creation of a fresh channel, conditional branch, and creation of non-deterministic integers. For technical convenience, we separate the arguments into two parts, integers and channels. For example, let's consider the Fibonacci process. The process in the first and second lines represents a function server that computes the nth Fibonacci number in parallel and returns the result to the channel R. The process in the last line sends a request for computing the mth Fibonacci number. We will explain our approach through this example. Next, we will present a basic translation from the pi calculus to a sequential language. Our idea is to convert each chain of communications on replicated input channels to a chain of function calls. A replicated input is transformed to a function definition. On the other hand, a non-replicated input is ignored and just transformed to a non-deterministic instantiation. We convert an output to a function call. The parallel composition is transformed to the non-deterministic choice. For example, we consider the Fibonacci process. This replicated input process is transformed to this function definition. The output on the channel Fib are converted to the function calls. On the other hand, the non-replicated inputs, like these, are ignored and transformed to the non-deterministic instantiations. The outputs on the channel R are just converted to skip because there is no replicated input on R. Now, let's consider why the termination of the process follows from that of the sequential program. The Fibonacci process has a chain of communications on the channel Fib like this. By the basic transformation, the sequential program has a corresponding chain of function calls like this. Now, this sequential program is terminating, that is, there does not exist an infinite chain of function calls. Therefore, there does not exist an infinite chain of communications on the channel field in the process either. As a result, we can conclude that the process is terminating too. Next, we will explain an improved translation using refinement types. At first, we discuss a weakness of the basic translation. The basic translation loses information about values received by non-replicated inputs. For example, let us consider this process. The process in the first line works as a function server that receives an integer n and a channel R, and then sends n-1 to R. In the second line, this x is equal to n-1, so the first argument of f monotonically decreases until it becomes negative. Thus, the whole process is terminating. By the basic transformation, we remove this non-replicated input, so in the transformed program, we do not have information about the value of x. Therefore, x is replaced by a non-deterministic integer. The transformed program is not terminating because there is an infinite loop like this. Next, we will explain a solution to address the weakness. We recover information about values received by non-replicated inputs using refinement channel types. A refinement channel type is given like this. This type describes channels that are used for transmitting both integers x tilde that satisfy a formula phi and channels of types kappa tilde. Let's revisit the previous example. The channel pred has this type. It is because the channel pred is used for sending an integer n and a channel R, which is used for transmitting n-1 that is smaller than n. And then we can assign this type to the channel S. Next, we define the transformation relation for non-replicated inputs. In the transformed program, we insert this assume statement according to the refinement type. Finally, the transformed program becomes terminating. Next, we will show you the refinement type inference via CHC solving. We can reduce the refinement type inference to a problem of CHC solving. First, we prepare these templates based on the simple types. Here, P1 to P4 are predicate variables. Next, we generate these CHCs from the typing rules. The first constraint comes from this output in the first line. The second constraint comes from this then part. The third and fourth constraints come from this else part. The last constraint comes from this output in the last line. There are various tools for solving a problem of CHCs. This is an example of a solution by a CHC solver. Using this solution, we can gain a terminating program. Next, we will show you a pitfall in the refinement type inference and a solution. A typical CHC solver returns a trivial solution which instantiates all the predicate variables to true. It is because the head of every CHC is an atomic formula on a predicate variable. Using this trivial solution, our transformation yields a non-terminating program because there is an infinite loop like this. So, in order to prevent this infinite loop, we add this extra constraint. A CHC solver returns x is smaller than n as a solution for P2. Finally, we can gain a terminating program. Next, we will report an implementation and experiments. We have implemented a termination analysis tool for the pi calculus. First, we inferred refinement types in a pi calculus process. The backend CHC solvers were spacer G3 and Hoyce. Next, we translated the pi calculus process to a C program. Finally, we used Ultimate Automizer as a termination analysis tool for C. Results of experiments are shown in this table. The test cases consist of two categories. One is taken from typical, and the other is prepared by us. We have run our tool and typical on these test cases. For the first category, our analysis fails in these four test cases. It is because we cannot make reasoning about synchronization over multiple channels. It is left for future work to extend our approach to treat the synchronization. For the second category, the refined method outperforms typical. For example, our tool can verify the termination of this process, but typical cannot do so because typical supports only the standard order on natural numbers as a well-founded relation on termination arguments. Finally, we will discuss related work and conclude. Our work is inspired by Deng and Sangiorgi's type systems for termination analysis. The key insight is that values of messages monotonically decrease in every chain of communications. Typical is a termination analysis tool for the pi calculus, but it can only verify termination of processes where natural number arguments monotonically decrease. There have been some theoretical work for termination analysis. In conclusion, we have proposed an automated method for reducing termination verification for the pi calculus to that for sequential programs. We have improved the basic translation using refinement types. We have implemented an automated termination analysis tool for the pi calculus. Future work includes a further refinement of our reduction and applications of our method to other concurrent languages. That's all for my presentation. Thank you for listening.